The next allotrope of carbon we're going to be going over is graphite. And you may not know what that is, but assuming you're using a pencil and taking notes, you are using it right now. Graphite is what we know as pencil lead. So, this is the chemical structure of graphite. You can see that it forms in hexagonal-like plates of carbon bonded to each other. Now, if you've ever wondered why, when you use your pencil, it leaves behind a trail of almost black powder, if you will, it's because of the way that graphite forms. So this you see one individual layer of graphite. However, once you have a bunch stacked on each other, these layers are not bonding to each other. The only thing holding them together is a thing called the London dispersion force. And it's strong enough to keep them together if they don't have a certain amount of pressure put on them, but they're weak enough that if you try to use them on your paper, these layers will slide past each other and will leave a trail on your paper. So graphite only has two remarkable properties. One is unusual softness because this is London dispersion force, and the second is its conductivity. The reason why is because when these carbon atoms bond, they form another special type of orbital, like almost like a hybridized orbital, but not exactly. What happens is that delocalized electrons not form, but the electrons that are in these atoms become delocalized, which means that they're being shared by two or more atoms. So because of this, electrons can move freely around graphite.